Yeah. Okay, great.
Yeah, because we are gonna have people, I mean, not most people, a lot of people are attending, but yeah, still we like other faculty to watch it after.
Yeah.
So, okay, in the interest of time, we should probably get started. Thank you everyone for showing up on this unusual Monday noon seminar. We are happy to have a speaker from Stanford, Connor Lawless. Connor has a bachelor's degree from University of Toronto, so he is used to cold weather. And he did his PhD at Cornell and has been at Stanford for the last year and a half. And he's gonna give a seminar on really interesting subject, which is a human-centered AI using an optimization approach. So we look forward to the interesting things that he's gonna tell. So let's have a welcome to our speaker. Thank you.
Thank you so much, and thanks for battling your way through the career fair to come here. Super appreciated. So today I'm going to be talking about some of my recent work at this intersection of machine learning and optimization, hopefully convincing everyone here that the synergies of these two tools can help us build more human-centered systems for AI. The papers I'll be talking about today were joint work with a whole host of really amazing collaborators at Microsoft Outlook, Microsoft Research, and UC San Diego, but I'll try to shout them out as we go through today's talk. Okay, there we go. So hopefully I don't have to work too hard to convince this audience that analytics tools like optimization and machine learning have been incredibly transformative pieces of technology, right? Even in just the past few years, we've seen these tools used to deliver food through the UN World Food Program, schedule classes at large universities during the pandemic, and even catch poachers in wildlife preserves. But behind all of these really impactful applications of analytics, there's always been kind of one crucial limited resource, which is access to the analytics expertise itself. Right? Behind all of these projects, there's a Jeff, there's an Alberto, there's a Carla that can take these complex real-world problems and translate them into something tractable that we can analyze and solve, or who can train a powerful predictive model and then work with domain experts to the point where they feel comfortable deploying them. And unfortunately, that expertise is becoming increasingly hard to come by. So for instance, we can zero in on something like optimization and look at the users of Gurobi, which is a leading solver for mixed integer linear programming problems that runs this awesome annual state of mathematical optimization survey, where they found that over 80% of their users have a graduate degree, over 50% of those users have a degree specifically in operations research, and maybe as a consequence of these high technical barriers, almost 100% of the survey respondents reported that OR expertise at their companies is either steady or growing. And Gurobi isn't the only ones to notice these high technical barriers of entry. Laura and Thibault have this really great survey paper that came out in IGDS last year where they kind of compare the explosive rise of machine learning to optimization and argue that these technical barriers are part of the reason why optimization just hasn't seemed to taken off in the same way. It's always a little stressful paraphrasing somebody's paper in front of them, so feel free to heckle me if I mischaracterized it. But the takeaway I really like from this paper is, a key to success going forward is going to be to lower the barrier of entry for users without advanced degrees in OR. Great. So on one hand, we have a tool like optimization, arguably pretty inaccessible. There's a reason why people pay a lot of money to come to places like UW to learn how to model and solve integer programs. But in some sense, it's inherently trustworthy, right? Once we've done this hard work of writing down a myth model, we kind of know the rules of what our solutions are going to look like because we've encoded that into the model. On the flip side, we can look at a tool like machine learning, which is becoming increasingly accessible, right? We can teach undergrads how to code neural networks in 3-4 lines of code without having to understand a lot of the internals or the math. But this level of accessibility also comes with a lot of challenges in terms of trust, especially when deploying these models. And part of the reason why is that a lot of modern techniques in ML require these big black box neural network-based approaches that are pretty inscrutable. Right? And this lack of transparency can have pretty bad impacts. So you might have heard of this story where a black box predictive algorithm kind of inadvertently kept somebody in jail, denied them from getting released. These tools have also been shown to be racially biased. So for instance, in another criminal justice setting, a black box tool was shown to inadvertently discriminate against black defendants. And because these models are so complex and inscrutable, a whole new field of research has popped up just trying to understand what sort of outputs we can expect these models to do. Trying to avoid these cases where Waymo using an automated neural network model inadvertently hits a bodega cat. And what all of these negative examples do is they really start to undermine trust folks have in deploying these models specifically in high-stakes settings. And this isn't just a hypothetical. A recent survey found that only 21% of US executives actually have trust in the analytics models they use. And Bonnie Muir, who's a psychologist at my alma mater, University of Toronto, has this really great quote where she says, decision aid, no matter how sophisticated or intelligent, however well it does on the benchmarks, it's going to be rejected by a decision maker who does not trust it. And this might seem like a really timely quote, but it's actually from a paper she wrote back in the 80s, which just shows you how persistent these challenges are in adopting these kind of advanced decision-making tools. So at a high level, what my research tries to do is close these kind of fundamental gaps between all the amazing tools we built for analytics and optimization and machine learning and the domain experts we actually want to use these tools. And I like to think of this as trying to design interfaces for this last mile of analytics practice that are getting these in front of the users we want. As you can imagine, this is a pretty interdisciplinary challenge. So my research generally falls at the intersection of three big buckets: optimization, machine learning, and human-computer interaction. And so far, my research is focused on two big thrusts towards these directions. The first is focused on leveraging recent advances in machine learning, like generative AI, to help make optimization models more accessible, so enabling those non-expert users that might not have a PhD in OR to get all the benefits of optimization. And like any good academic, I'll do a bit of shameless self-promotion, which if that research direction sounds interesting to you, we just ran a 4-hour tutorial on it at AAAI a couple weeks ago, and all the materials are public. So if you're a PhD student, it's a good one-stop shop for getting started in the space. And then the second big thrust of my research goes the other way. So it leverages tools from discrete optimization, like integer programming, to build machine learning models that are inherently trustworthy by design. So are interpretable, have some guarantees on fairness, and we can use those tools to build better auditing tools for checking the behavior of these models. So a quick roadmap of where I'm going to go for the rest of today's talk. The first half is going to focus on that first research direction, so showing kind of some of our recent results on using LLMs to enable non-expert users to model and solve their own optimization problems. We'll see this first in the context of meeting scheduling, which is a collaboration with Microsoft Outlook, before talking briefly about more general purpose systems we've built for mixed integer linear programming problems. And then in the second half of the talk, we'll focus on that other direction and talk about some LP models that we built for auditing machine learning models for a very specific kind of bad behavior, which is algorithmic preclusion. So to kick us off, the question I want to keep in the back of our minds for the first half of this talk is, can we democratize access to optimization? Right? Can we get all the benefits of optimization without needing an OR expert in the room? Now, it's a trendy way to phrase this question, but this isn't a new problem, right? You could argue enabling non-expert users to make better decisions is kind of a foundational quest within the field of operations research, going all the way back to work on decision support systems from Keenan Morden in the 70s, to more contemporary approaches that have brought non-expert users into very structured components of the optimization process, whether that be multi-objective optimization frameworks that help these non-expert users reason about trade-offs between different objectives, or even interactive optimization paradigms that bring users into the optimization process itself, guiding heuristic search, or querying those users for kind of missing pieces of information in like a constrained programming model. Similarly, you can view a really rich line of work on algorithmic selection and configuration as being an attempt to enable non-expert users to do better algorithm design, starting with work from algorithm selection from Rice in the 70s to more contemporary machine learning-based approaches for these problems. But what I'd argue is that existing approaches to bring non-expert users into the optimization process have really had to focus on very structured components, right? Either picking between a couple of objectives or configuring a solver you have. And I already gave away the punchline in the intro to the talk, but what I'm hoping to convince everyone in the next 20 minutes or so is that generative AI presents a really, really exciting new opportunity to revisit the scope of what we allow non-expert users to interact with. Right? And we've already seen some really positive examples in the recent literature where generative AI has been used to bridge these technical expertise gaps in traditionally technical domains, things like coding and SQL, as well as even traditionally creative tasks like writing. So the more specific question we're going to be trying to answer is, can we leverage generative AI to do this democratization? Now, if you buy the premise that this is an interesting enough question to spend the next 20 minutes or so talking about, then I think a natural follow-up is, what exactly are we trying to democratize? Right? How do OR practitioners actually go about solving real-world optimization problems? This might seem like a pretty foundational question, but much to our surprise, there's been kind of very little grounded scientific work trying to understand how optimization is practiced. There's a lot of anecdotes that trickle their way into the intros of OR papers, but nothing comprehensive. And why is that important? Well, if we compare this to something like machine learning, a big chunk of the whole field of human-computer interaction has spent the last 10 years or so trying to understand how virtually every aspect of data science is practiced. Everything from how practitioners document their data, to how they implement statistical machine learning tools, to how they work with data. And a consequence of this is that it's led to the development of frameworks and tools that are shaping how data science is practiced. So you might have heard of things like model cards and data cards that are becoming industry best practice in terms of how folks document their data or the limitations of these pre-trained models. You might have heard of something like Game Changer, which is a user interface that allows domain experts to integrate their knowledge directly into the training of these machine learning tools. But what I really want to hit home is that there's this big kind of gap between what we know about how data science practice and what we know about how optimization is practiced. And I think that gap is what's limited a lot of development of these more human-centered tools. So motivated by this shortcoming, we actually just wrapped up a few months ago to the best of our knowledge, the first qualitative study of optimization practitioners. So we recruited 15 participants from 7 different industries, which resulted in over 650 minutes of interview transcripts, which we then analyzed using grounded theory, which is a toolkit from the HCI community. And I won't walk through all the findings. I think if you're a PhD student, it's a really nice paper to read because it identifies a lot of open problems in terms of tooling for OR practitioners, where I think we can make a big difference in terms of how usable these systems are. But what I want to summarize is kind of the high-level process that we found and identify some pain points that we're going to try to address in the papers I'll talk about today. So hopefully this workflow is going to ring true for a lot of folks that have done applied work. But at a high level, the process most OR practitioners do when they're solving these applied problems is first they have to spend a lot of time understanding decision-making problems, right? Typically, OR experts are not experts in the domain in which they're building models, right? Maybe you're a UW grad who now needs to work on some sort of steel manufacturing line. You've never worked with steel manufacturing before, so you have to spend weeks, if not months, meeting with people at these steel manufacturing plants to understand what that workflow is, what the constraints are, where can optimization even make a difference. And because everyone's time is limited and because you're usually working from scratch, this can take a ton of back and forth. Once you have that understanding, you then have to translate that into an optimization model. This is a really pragmatic process. It usually requires making these trade-offs between how faithful that model represents that real-world problem versus what can we actually solve in a reasonable amount of time. You then have to tune that model for efficiency. That can be something as simple as creating better parameters for Gurobi when you're going off to solve it, or something as complicated as applying decomposition algorithms or coming up with custom primal heuristics. And then even after you've done all this hard work, you then have to validate that that optimization model is actually solving what you think it is. And typically what happens is you go and you show a sample solution to this domain expert, and they suddenly realize tons of constraints that you missed. That would mean this solution is impractical, and you have to repeat the whole process. And really, this iterative nature of this problem can be a big bottleneck, not even for just developing models, but also maintaining them. Right? You can imagine the same workflow happens as these optimization models apply over time. And unless you can employ an OR PhD student to constantly be working on your problem, a lot of these models get outdated and, if not, discarded altogether. So the big problem we're going to be trying to work towards is can we remove these really slow feedback loops and take an OR expert out of this process and enable these non-expert users to do these model refinements themselves. So we're going to study this first in the context of meeting scheduling. So this is a paper that was in collaboration with Jacob Schofer, who's now at the University of Groningen, as well as a whole bunch of folks on the Microsoft Outlook team that helped us integrate this into their product, as well as some folks on Microsoft Research. So to ground this in a very practical setting, I want us to think about meeting scheduling. Hopefully I don't have to work too hard to convince folks here that meeting scheduling is kind of a painful, mind-numbingly boring task, right? And it's a task that's faced by pretty much every information worker in the US. But one thing that was bugging a lot of folks at Microsoft is that even though we all agree that meeting scheduling is a pain, the tools that they were building to help people do meeting scheduling were pretty criminally underused. So maybe as a quick show of hands, how many folks here use Microsoft Outlook? Okay, pretty good customer base. How many folks here have used Microsoft Outlook's time suggestion tool? Okay, so that's actually pretty in line with what they saw. So they ran a user study. Actually, I should say, for those of you that haven't seen the time suggestion tool, the way it works is when you go to Microsoft Outlook to schedule a meeting, you type in who you're going to meet with, and it pops up some candidate times of where it thinks that meeting is going to land. So in a perfect world, you get to click one of those buttons, your meeting is scheduled, and you don't have to do any future work. But they ran this massive survey of Microsoft Outlook users and found that essentially only 13% of users were using this service. And a big chunk of the reason why is it's not necessarily the most accurate. Right? It only guesses where a meeting is going to land correctly about 32% of the time. But I'd argue that's actually not a bad number given how complex this task is. But even if we drill into the 32% of the time where it correctly guesses where a meeting is going to land, users still default to manually scheduling that meeting over 90% of the time. So they see an oracle telling them where they're going to schedule a meeting, and then they still decide to look through everyone's calendars anyways. So why is that? Well, they ran our user survey and essentially found that users were really frustrated by the lack of agency or control they had over these systems. So you can imagine in a setting like meeting scheduling, there are a lot of preferences that go into where you want to schedule a meeting. So for instance, one user complained that they couldn't adhere to things like a meeting-free Friday. They wanted to tweak time suggestions to their specific needs, or in these over-constrained settings, wanted some insight into how to relax scheduling constraints. Okay, so if we know users want to be able to integrate custom preferences, a natural follow-up question is what sort of preferences do people want to integrate? So while I was at Microsoft, we ran a diary study with over 100 participants from within Microsoft to try to understand what sort of preferences would folks want to be able to integrate. So when they went to schedule a meeting, they would tell us what preferences they want to be reflected in a tool. And I'll keep the takeaway pretty high level, but essentially the kinds of preferences users want to integrate are incredibly diverse. So here's just one response from one user for one meeting they were going to go to schedule, and you can see an almost laundry list of things they want to be able to integrate, right? Things like time zone, business hours, holidays, lunch hours, same building, whether or not they are both working hybrid. And this is before we get even into like meeting-specific information, like if I have 3 hours of meetings back to back, I want a break. And why is this a challenge? Well, it means that existing kind of user interfaces for these sorts of personalization just aren't going to cut it, right? So if you've used a Microsoft product before, you know kind of the modus operandi is if you want to add some sort of personalization, you're going to add a drop-down to capture that personalization, right? So in the time suggestion tool right now, they have like a very simple drop-down that just says, preferences on timing and duration. But unfortunately, no drop-down is going to exist that's going to capture all the kinds of preferences that people want to be able to integrate. So the question we try to answer in this paper is, can we use LLMs as a tool for translating these incredibly diverse scheduling preferences combined with traditional OR tools to provide and kind of improve decision support in the setting? So before I jump into the system that we built, I want to highlight kind of two naive approaches and highlight why they fail in the setting. And the first is just to give it all to an LLM. So we started working on this back in 2023, so the trendy LLM at the time was GPT-4. And what got folks at Microsoft super excited is that in the press release for GPT-4, they had this cute demo where you could just put a paragraph of text about your availability, and it would pop out when a meeting is going to schedule. OK, so maybe this isn't a hard problem at all. We just need some sort of API on top of an LLM. We give them all the information, and the LLM will do the scheduling for us. So we ran some initial experiments where we constructed 10 synthetic scheduling scenarios with 3 very simple preferences and constraints. So things like wanting to meet between 11 and 3, not wanting to meet on a Friday, preferring to meet on Tuesday or Thursday, things like that. And what we did is we implemented kind of ground truth correct versions of these optimization models in a constraint programming solver. And you can think of this y-axis as being normalized to 100%. So this is the most number of constraints that could be satisfied. So we want to aim towards 100%. And then we took GPT-4 for a spin on this problem. So I say GPT-4 native, but think, substitute it in your favorite prompting strategies of choice. And what we found is that it could only recover about 70% of the best possible constraint satisfaction, right? So a massive gap between, an optimal solution and what these LLMs popped out. And maybe in hindsight, that's not super surprising because there's been a lot of concurrent work since then that have shown that LLMs are bad at these constraint satisfaction tasks, right? We've spent the last 40, 50 years learning how to do very good constraint satisfaction solvers in the OR community, probably to our benefit that just giving it to an LLM is not able to replicate the same results. OK, so that's one approach, just an LLM native. The other thing to think through is why do we need ML at all? Why can't we just use traditional optimization approach? So if you haven't seen it before, the paradigm for optimization we're going to use is constraint programming. It's a pretty simple setup. In constraint programming, we have a bunch of variables, each with an associated domain. We have a bunch of functions called constraints that are just going to map from a setting of those decision variables to an associated score. That score can be infinite if that constraint needs to be satisfied. And our objective is to find the setting of those decision variables that are going to give us the best kind of aggregate score across our constraints. And meeting scheduling is a really natural fit for this problem, right? We can think of our variables here as being a meeting time. If we're scheduling a recurrent meeting or we're scheduling a whole portfolio of meetings for an individual user, we have multiple decision variables. Our domains could be any time blocks of the correct duration over the next horizon, so like 1-hour meetings over the next 2 weeks. Constraints can capture any sort of user preference or meeting requirement, things as simple as Connor needs to attend this meeting, to something as complex as if I have 4 hours of meetings back to back, I need a break. And to be a little informal, our goal here is to find the best time. So why doesn't just this constraint programming approach alone work? Well, again, we don't know what these constraint functions for a user are a priori. And the challenge in meeting scheduling is that these preferences are often constructed in the moment. So they're very contextual. So we can't expect to do this offline elicitation where we just ask someone exactly for what their preferences are and run that for every meeting they schedule later, because those preferences are going to change based on what meeting they're scheduling, right? Like maybe I don't like meeting in the morning, but if I'm meeting with Madeleine, who's signing my paychecks, I'll meet in the morning if that's the only time that works for her, right? So you need something that's kind of in the moment. So the key behind this, the system that we built is that we're going to try to get the best of both worlds. So we're going to use LLMs as a tool for flexibly handling the diversity of scheduling preferences and the fact that they need to be elicited in the moment, but we're going to use a constraint programming solver to do the actual constraint satisfaction problem. So trying to get around both of the failure cases. And I will say that there's been a lot of concurrent work since, but this was actually the first system that looked into this like hybrid combination of optimization and large language models. So what does the system look like? Well, at its heart, we're going to have a constraint programming model that we're going to represent as a prioritized list of constraints. So remember before I said you have some associated score for meeting a constraint. In practice, that's not the best way from a human-centered perspective on how to construct an optimization model. Folks are terrible at giving an exact numeric value for how important it is to meet a constraint. So in some initial user studies, we found that this prioritized list kind of aligned with how folks were thinking about this. So we're going to satisfy constraints with higher priority before constraints with lower priority. And we're going to represent each of these constraints with a Python function. Now, in our setup, this is just going to be a Python function that takes in a candidate meeting time and some additional data points and APIs and outputs whether a Boolean value of whether or not it meets the constraint. But you can also imagine settings where we substitute in a specific solver code, like Google or tools. We're then going to take this constraint programming model and send it to a CP solver to generate a refined meeting time. And essentially, all these LLM pieces are going to act as a layer on top of this model to facilitate these non-expert users to customize that approach. So we're going to have a chat bar where users can specify things like, I'd prefer to meet on Thursday. We have one LLM-powered component that translates that chat message into one of 5 pre-specified tasks that it can take. One of those is adding a constraint, which calls another LLM agent that's going to take this natural language preference, embed it as a Python function, and add it to our list. We can also do other simpler operations like deleting a constraint, changing the priority, or generating a suggestion, which is going to call that CP solver. One nice thing about this framework is we also give it the flexibility to message users. So one kind of recurring problem is when you're working with users specifying decision-making problems, they're very bad at specifying it at the level of concreteness you need to actually construct a model. You might say something like, I want to meet when I'm productive, but it's not necessarily clear what that means. So giving this system the flexibility to query users to refine information actually turned out to be a really big game changer in our user study. But yeah, that's kind of the high-level idea. LLMs is a translation layer, but we're going to have an underlying optimization approach. OK, so I do have to give a bit of a disclaimer. I know there's a lot of optimization enthusiasts in the crowd. And I will say this is not a tough optimization problem, right? If you think of something like meeting scheduling, if we're only scheduling a single meeting, there's only so many one-hour meeting blocks over the next few weeks. People tend not to want to schedule things to the millisecond level. So it's a pretty finite domain. And the number of constraints we're looking at is usually on the order of 5 to 10. So we can kind of enumerate all of these meeting blocks, score them all, and just pick the best. So not using any sort of sophisticated solver, but the same principles are going to underline more complicated systems that we built for mixed integer linear programming problems. So same ideas, just in this setting, we lucked out, and it's an easier problem to solve. OK, so what does all this added complexity get us? Well, if we return to those initial synthetic scheduling scenarios, it's actually going to let us close the gap between these LLM approaches alone and the best we could have gotten if we had a team of software engineers implement this constraint programming model. Now, maybe you're unconvinced by 10 examples. That's not a really good, robust benchmark. So what we did is we actually took that diary study that we ran earlier, where we had solicited all of these scheduling preferences, and we turned that into an evaluation data set. So we did some post-processing to kind of augment the size of it. So if we had like special keywords like Tuesday or Thursday, we would randomly in-sample those to kind of grow it automatically. We also used different LLMs to rephrase these to get some linguistic diversity. And then we took 2, at the time, state-of-the-art LLMs for a spin on this problem, GPT-3 and GPT-4. I won't walk through all of these numbers, but I want to highlight 2 nice bits of promising information that show that this is a worthwhile paradigm to focus on. The first is this compilation rate. So this is saying, of these Python functions that we've generated, what fraction actually run? And we can see that that number is close to 100%. Right? And this is a number that's only gotten better since we ran the study back in 2023, or could get better by substituting in a coding-specific LLM or fine-tuning something on this task. So think of this as a lower bound for how good this system can be. Next question is like, OK, we're getting code that runs. Is it correct code? So what we did is we had a team of software engineers actually implement ground truth correct versions of all these scheduling preferences. And now you can imagine we have almost a binary classification task. I give you a pool of candidate meeting times. I have our expert implemented function that says for each time whether or not it meets a constraint. I have our LLM generated one, so we can look at things like precision and recall. And again, these numbers are pretty close to 100%. And you can imagine it's actually hard to get exactly 100% because there is some inherent ambiguity, right? Like if I say I don't want to meet in the morning, does that mean I don't want to start my meeting in the morning? It needs to finish before, or, afternoon. There's a lot of ambiguity. So I would actually be pretty bullish that this is even higher than 95%. But some nice initial evidence, at least from a quantitative perspective, that LMs are good at this translation task between natural language and these more concrete embedded constraints. But this just gives kind of like one piece of the puzzle, right? What do we care about is helping people schedule meetings better. So to measure that, we actually built a prototype system. So this is in collaboration with Microsoft Outlook, so it looks very similar to Outlook or Microsoft Teams. So we have some calendar information, and then this chat bar. So at this time, this chat bar was unnamed, but now it's since been called Copilot, and you've probably seen it in all of your Microsoft products. But this is just going to wrap all the functionality that I've talked about so far. And we did a pretty small-scale user study. So we recruited 10 participants, each to sit with us for a whole hour and run through various scheduling scenarios. And the goals were twofold. The first was to try to characterize how preference construction can kind of change in response to these dynamic suggestions. This is actually something that was really hard to do for past folks in HCI literature because you didn't have this tool that could actually concretely reflect these updates and preferences, right? You either had to have this synthetic scenario, or somebody would kind of do it behind the scenes, or the level of personalization would be really small. So our HCI collaborators were super excited to use this as a research tool. More importantly for me, I was really interested in this idea of usability, right? So when we're designing at this intersection of LLMs and optimization, what are some design recommendations we need for future systems? So I won't walk through all the results. We have quite a bit of qualitative analysis of these findings, but I want to highlight 3 takeaways that I think are going to be important for this audience. The first is that across the board, people love the system, right? So if your baseline is no personalization or very, very simple personalization from these dropdowns, then being able to kind of recommend any sort of preference and have that reliably reflected in future time suggestions was a completely different paradigm. But it does come with a few challenges. The first is that users found this chat modality really burdensome. You can imagine if you have a ton of preferences you want to be able to embed in this optimization model, eliciting them all by text, especially if you're doing that for every meeting, can be really slow. But I think this just points to a really interesting future research question, which is how can we warm start these systems, right? So if you're Microsoft Outlook and you have months of scheduling behavior, can we infer what these preferences are just based on past scheduling behavior, so we only have to elicit smaller pieces of this contextual preferences in the moment? And then kind of a bigger red flag for this whole kind of hybrid LLM optimization system is that users found them very difficult to debug, right? So you can imagine if you have an LLM that's embedding a Python function, if something goes wrong, so that LLM screws up an inequality, then it's hard for users to diagnose what the problem is if they can't look at the underlying Python function. So in a meeting scheduling context, there's actually some really nice visual workarounds, right? If I embed a preference, I can show you visually what that looks like on your calendar, and you can even manually adjust kind of the time gaps. But for more general MIP models, it's kind of an open research question of how we can enable this debugging and validation. Great. So I like meeting scheduling because it's the kind of optimization model that I interact on a pretty daily basis with. But I want to underscore that this idea of iteratively eliciting problem specifications from user is kind of a hallmark of applied operations research. So since this project, we've been working with a lot of industry practitioners and kind of 3 different applications that have the same kind of flavor to them. The first are power systems. So here we've been working with folks in the civil engineering department at Stanford about applying this to grid operators. So there they might have some sort of contingency scenarios that they want to run. Like say I know it's going to rain a lot in San Francisco. This is kind of my understanding of how it's going to impact the grid. How's that going to impact generation? So that's one kind of embedding. Another is in school zoning. So we've been working with Irene Lowe, who does a lot of work on these school districting problems. And here you can imagine that it's a really big distributed decision-making problem. You have a bunch of parents that have preferences that they want to be embedded into how these school catchment zones are designed. The policymakers at the SF School Board have a lot of these kind of insights into what these boundaries should look like. So typically required a lot of back and forth between model developers and these policymakers. And then finally, you can even imagine just more complicated versions of scheduling, right? So instead of looking at an individual meeting, things like nurse scheduling in a hospital setting. The only big difference between all these applications and the meeting scheduling context is that the complexity of the underlying optimization model is much larger, right? If we were thinking of power systems, these are usually unit commitment problems, so they're much gnarlier MILPs than these solved by enumeration constraint programs. But the same principle of taking this larger modeling task and breaking it into these smaller components and using LLMs also translates into this more advanced modeling domain. And you don't have to take my word for it. We built a system at Stanford called Optimus, and it has an associated web app, so you can play around with it yourself. But the key idea is that that decomposition of what those steps look a little different. So here, these steps more kind of align with the process of building a MIP model, so like first extracting things like constraints and objectives in natural language, then translating them into a LaTeX formulation, then implementing them in Python and calling Gurobi, and executing and debugging. So the steps look different, but the same kind of design principles apply. And for PhD students that might be interested in this area, a big effort of this Optimus project is trying to build open source resources to support future development. So one big part of this effort has been building a data set of problems to benchmark these systems on. So it's released on Hugging Face, but essentially we put a lot of work into collecting natural language, MIP model, code kind of triplets. Some of them are industry grade, or I like to think of them as industry grade. So they were taken from the Informs Journal of Applied Analytics, and we had some PhD students actually implement the models and synthetic data so that you can run the models. The other thing I'll mention is that web app that I talked about is all completely open source. So let's say you have like a rockstar idea for improving maybe that model formulation phase, so working towards building stronger MIP models automatically. All you have to do is substitute in one API endpoint, and you get all the benefits of a web app to do kind of experiments with users. And if anyone wants to get running with this, more than happy to chat offline. The other thing I'll flag is, we started working on this back in 2023, and at the time, the combination was novel, but there's been a ton of work in this space since, focusing on kind of extending this to more general constraint programming settings, applying this in even an educational context, and even integrating this with multi-objective optimization. So, it's a very, very cool and exciting time to be working in this space. I also will flag, and happy to chat about this more offline, is even though we've been focusing on LLMs as a tool for doing this translation to a concrete optimization model, there's also a lot of other areas where we can leverage this natural language information to do better optimization. So for instance, we have this cute paper that uses a natural language description of the optimization problem you're trying to solve to do better solver configuration. So specifically figuring out which cutting plane separators to turn on in something like Gurobi. And we found that even in this simple framework where we're only touching one set of parameters, we can get up to 70% improvements over something like skip or Gurobi defaults on a problem-specific basis. So a lot of cool opportunities to revisit how we're doing optimization with this added kind of natural language information. Great. So maybe before I move to the second half of the talk, this is a natural point if anyone has any questions or kind of clarifications about this first line.
Yes, just a second.
Okay, good. So I see the vision, but maybe you could talk a little bit about the actual meetings, because then you kind of swapped over to this preference solicitation stuff, right? That's also got a huge tradition in OR and also in human factors on how to do preference solicitation. For the tool for Outlook, right? I'm assuming it wasn't all just one-on-one meetings, right? That's trivial. What are we talking about in terms of how many schedules that needed to be coordinated, and what kind of meetings are we talking about? Different meeting lengths, or what's the nature of the different test cases that you looked at?
Yeah, so for the user study that we ran, we tried to build kind of 5 representative scenarios of use cases we saw at Microsoft. So that varied from a one-on-one meeting to something like a large, department-wide 20-person meeting, 30 minutes to 2 hours. We did have some privacy concerns, so all of our user studies, people couldn't interface with their actual data, so they are kind of synthetic in some sense. But one of the scenarios was asking them to schedule think of a meeting that they had to schedule recently and to do it in our system. So the underlying calendars they were interacting with were synthetic, but kind of representative of their use cases. And a lot of the people we recruited for this study were admin folks who, scheduling is their bread and butter, as well as some software engineers and some PMs.
Any other questions at this point?
You mentioned that GPT-4 obtained like a 68% accuracy with respect to constraint violation. How do you think, do you have any insights with respect to new models like GPT-5? How you expect that to increase?
Yeah, so for this Optimus project, the more general MILP model, the most recent version of that paper, we benchmark on O3 and GPT-5. And essentially, the takeaways are the same, but the magnitude is different. So these like decomposition frameworks always provide an improvement over the base model. For something like GPT-4, it was like 40, 50%. For something like O1 or GPT-5, that's more like 15%. But there always seems to be a value in these like decompositions versus these one-shot approaches. And there's also some nice HCI benefits of if you decompose this task, there's more natural points for people to kind of intercede.
Okay, thank you.
Great. So maybe we'll move on, and if anyone has more questions, we can circle back at the end. So the second half of today's talk, I want to go the other way. So instead of talking about LLMs as a tool for making optimization more accessible, I want to focus on how we can use tools from discrete optimization to do better model auditing or build more trustworthy machine learning algorithms. So the paper I'm going to be focusing on is joint work with Lily Wang and Burke Houston at UC San Diego, as well as Madeleine Udell at Stanford. So the setting I want us to think about is when machine learning is used to automate decision making. So this is becoming kind of an increasingly common use case in things like finance, where you might have a historical database of loan applications and whether or not they were successful, so people were able to repay. And you might want to train a machine learning model to say, given a new credit loan application, is this person going to be able to repay their loan? Right? And the natural follow-up is we can then use that to automate decision making, and that now when we get a new applicant, we just run their report through an ML model, and if we don't predict that they're going to be able to repay it, we can deny them the loan. Now, because this is a high-stakes setting, right? Getting a loan can have a big impact on somebody's life. There's been a lot of kind of regulatory considerations over giving folks what is called algorithmic recourse. So that just says if you've been denied by an automated decision-making tool, we'll give you a plan for what you can do in order to change your outcome. Right? So we might tell someone that they have to get a PhD or improve their credit score in order to get their loan approved. Now, traditionally, how we design machine learning algorithms is that we don't take into account how users can actually go about changing their features. Right? We can ask someone to improve their credit score, but we can't ask them to decrease their age or their number of dependents. And unfortunately, what that means is that in practice, these machine learning models might assign folks what we call fixed predictions. So these are settings where an automated tool is going to deny someone a loan, and there's nothing that that individual can do in order to change their outcome. And in some cases, we might want to guard against this. In some cases, this is actually a desirable property, right? In something like content moderation, we want to make sure people can't game their way past the filter. But in general, we care about at least understanding what these cases are and when they come up. And unfortunately, this isn't a hypothetical. There's been some pretty kind of high-profile cases of these fixed predictions in the wild. So for instance, you might have seen this heartbreaking story about a patient in the UK that found out that an automated decision-making tool was going to inadvertently deny her from ever being able to get a liver, just based solely off of her age. Now, this isn't a new problem. So there's been a ton of work in the optimization community over the last few years on algorithmic recourse. Oftentimes focusing on trying to generate these recourse plans for different machine learning models or under different assumptions for how robust those outputs need to be or for what those data manifolds need to do. It's also really related to this field of strategic classification, which kind of goes the other way and tries to design machine learning models that prevent people from changing their outcomes. But what I'm hoping to convince everyone here is that existing work in algorithmic recourse has focused on one very specific paradigm, which is on a point-wise basis. So you give me an individual, and I tell them what the recourse is or whether or not they're able to change their outcome. And that's actually not the right way to think about this from a policymaking and model development perspective. And the reason why is that for one point, it's going to lead to us to miss these out-of-sample issues. Right? If we can only audit whether or not someone is assigned a fixed prediction if we have an individual, well then, if we don't have a representative database and we go to deploy a model in a new setting, then suddenly we're only catching these issues after we've deployed a model. And retraining a model or catching them in the wild is much more expensive than if we could catch them in model development. It also means that auditing these tools are really data dependent, right? If we want to figure out if these models are precluding people from getting a good, we need a lot of individuals to test these data. And this is actually really hard for external auditors. So we've been chatting with folks at the ACLU where there are some mechanisms in order to get these models once they've been trained in a finance setting, or you can imagine in a healthcare setting, a lot of these models are actually public. They're published as like risk scores or scorecards, but the data used to train them is not, right? So it's harder to run these audits. And then finally, from a model development perspective, it makes it really difficult to debug these issues, right? If I run your model through my tool and I tell you these individuals are being assigned a fixed prediction, it's hard to work backwards and understand what the defining characteristics of those individuals are that are causing the fixed prediction, right? So it leads to a lot of trial and error. So the key question we try to answer in this paper is, can we move beyond this pointwise paradigm and enable a tool that's going to allow us to characterize, well, if anyone is going to be assigned a fixed prediction under a trained machine learning model. So provide stronger guarantees for deploying these approaches. And the way we're going to do this is we're going to introduce a new paradigm where we try to verify recourse over an entire region of the feature space. So what does the setup for this look like? Well, first we're going to start with a characterization of our feature space. This has to be like MILP representable, but that's a pretty general assumption. We're also going to have within our feature space a region that we want to audit. This could correspond to something like any plausible loan applicant or subgroup of interest, something like any black female loan applicant. We're also going to have a bunch of actions, this universal action set, which are going to define how users can change their features. So in our paper, we focus on constraints that are defined by just the semantic meaning of those variables, like age can only increase, it can't decrease. But you can embed pretty much any sort of constraints you want. So if you have a causal model for how these feature interactions are going to impact each other, you can amend that as a constraint. If you want your resulting data to be within some sort of manifold of your data, you can embed that as a constraint as well. And there's been a ton of work in the MIP community on like different sorts of constraints and how to embed them. We're also going to have a binary classifier where a prediction of one is going to be a positive outcome, like you get your loan approved or you're able to get a liver. For the rest of the talk, I'm going to focus on a linear classifier, but time permitting, I'll chat about how all the machinery I'm going to introduce can be extended to pretty much any MILP representable function class. And then finally, the whole goal of this framework is to identify what we call our confined regions. So this is going to be a subset of the region that we're auditing such that all individuals are assigned a fixed prediction. You can imagine if the largest confined region we can find is the entire region that we're auditing, then we have a certification that nobody can kind of game the system. Everyone is assigned a fixed prediction. If we can't find any sort of confined region in the region that we're auditing, then we have a certificate that everyone has recourse. And I'll chat a bit more details in the sec, but essentially we're going to be trying to get these nice interpretable confined regions so we can help model developers correct these mistakes. Okay, so what does this new paradigm buy us? Well, it's going to let us close those gaps with these existing pointwise tools, right? One, it lets us preempt preclusion, right? If we can verify recourse over an entire region of the feature space, we suddenly don't have to worry about deploying a model and seeing these bad cases pop up live. It's also going to enable data-free auditing. If you have a public healthcare model that you want to see if anyone's going to be denied from, we can run it through. So right now we're working with some collaborators in Switzerland on applying to that UK liver allocation mechanism. And then finally, it's going to give model developers these nice interpretable outputs. Great. So hopefully everyone agrees this is a nifty paradigm, but the million-dollar question is how do we go about actually solving this paradigm? How do we go about finding these confined regions? And specifically, we're going to focus on finding one kind of region, which we're going to pick for interpretability regions, which are boxes. So quick refresh, a box, just a simple set defined by upper and lower bounds on our features. Why is this worthwhile to think about? Well, the nice thing about boxes is that because we just get these simple upper and lower bounds of each feature, when we print out what these regions look like, we get these nice interpretable outputs, right? Especially if we do some filtering on any kind of like vacuous upper and lower limits. And this has been a really popular function class within the interpretable classification literature. For instance, a big chunk of my thesis work was on learning these rule sets and classification settings. Okay, so we have a well-defined problem. We're going to try to find the largest confined box. How do we do it? Well, I'll give you kind of a flavor for how we set up this optimization problem. To warm up, we're going to start with a simpler problem, which is given a fixed box, how can we validate whether or not it's confined? Well, it turns out we can set this up as a pretty simple MIP. So we're going to have two sets of decision variables, one corresponding to the individual, one corresponding to the actions that they're going to take. We're going to add some constraints to ensure that that individual comes from the box that we're auditing and that the actions correspond to feasible actions in our actionability set. We're also going to have our linear classifier, and our goal here is to flip the outcome. So we just want to ensure that that individual plus the actions that they're going to take are going to give us the positive outcome. And in theory, we could put an objective here if we care about costs or some sort of other metric, but in practice, we just care about this feasibility problem. So note, one really nice thing is that by definition for a confined box, this problem needs to be infeasible, right? That's just how we've defined what a confined box is. So what we're working towards is we just want a set of constraints that are going to capture when this problem is infeasible. And we're going to start with an even simpler case, which is what if this is an LP? So we don't have any discrete variables. And just for notation, we're going to summarize this in a matrix form. Okay, so this is a pretty optimization-pilled crowd. So as soon as I said that we want to verify that this LP is infeasible, Farkas' name probably started echoing through your head, right? So quick refresh on what Farkas' lemma is. It just says that if we have a linear system of equations, then exactly one of two things hold. Either we can find a feasible vector for that linear system, or we can find this dual certificate that's going to guarantee that that problem is infeasible. Okay, and this is exactly what we want, right? We just want a set of linear constraints that are going to capture when these problems are infeasible. Fantastic. Okay, but there is a catch, right? Which is we do actually care about these MILP settings, right? So how are we going to extend Farkas' lemma to this discrete case? Well, we're going to actually employ a pretty simple strategy that's going to work well in practice, which is we're going to try to simultaneously find these dual certificates for all continuous restrictions of that optimization problem. Okay, so what's a continuous restriction? Well, it's just going to be our MIP program where all the discrete variables are fixed to specific values. Right? So if we have an integer between 0 and 100, one continuous restriction would just say that that variable is set to 1. Okay, so suspend disbelief for a second that we can enumerate all these continuous restrictions. If we could, how could we formulate this as an optimization problem? Well, pretty simple. So our variables are going to be U and L, which are going to define the box. Our objective is going to be trying to maximize its size, which we're just going to represent with these kind of normalized upper and lower bounds on each feature. And for each continuous restriction in our problem, we're going to try to generate these dual certificates, right? So this guarantees that any possible case of our MIP is going to be infeasible. Okay, I would imagine there's a lot of skeptical faces in the crowd, and why is that? Well, this number of continuous restrictions can be exponentially large, right? If you have a lot of discrete variables, then enumerating all these continuous restrictions can be pretty impractical. And this is already itself kind of a gnarly optimization problem in the sense that it has these quadratic constraints. So we're no longer in MIP land. We're looking at a MIQCP. But I will say, compared to a lot of work on integer programming for machine learning, this is a small scale setting in the sense that we're not scaling with the number of data points in our training data set. We're just scaling with the dimension of our data, and specifically the dimension of our trained machine learning model. So if we have a sparse linear model that only uses 5 features, then we're only really care about looking at those 5 features. So it's actually a pretty small in the realm of these ML for IP approaches or IP for ML approaches. Okay. So how do we go about handling these exponential number of continuous restrictions? In the interest of time, I'll just give you kind of a high-level view, and I'm happy to go into more depth offline. The first is that we're going to try to characterize a set of easy actionability constraints. So these are going to be a set of constraints that it's going to suffice to only look at a single continuous restriction. Here, the idea is that we prove that under this set of actionability constraints, the verification problem is actually totally unimodular. So it suffices to just look at the linear relaxation. So we don't actually have to worry about these continuous restrictions. We're good to go. And the really nice thing is that when I say broad class of actionability constraints, this actually encompasses pretty much all actionability constraints considered in the past literature. So there are multiple kind of papers in this field that turns out they didn't need to solve a MIP at all. They were really solving an LP. And despite the ubiquity of these algorithmic recourse problems, this is actually kind of the first such result. Now, unfortunately, it's not a universal result. So there are some sorts of constraints that don't have this nice property. But we can actually provide some pretty pragmatic guidelines. So as long as once we fix discrete variables, the resulting subproblems fall into this easy actionability constraints, then we're good to go. So in practice, what that means is that we can get away with only looking at a very, very small number of these continuous restrictions to solve the problem. So for instance, we looked at this FICO data set that has 48 binary variables. So if we enumerated every continuous restriction, completely intractable. But it turns out that we can get away with only fixing 2 of those variables and recovering these easy actionability constraint setting. So we can actually solve this with only 4 continuous restrictions in total, which still solves in a fraction of a second with something like Gurobi. And then finally, as soon as I said that we had some sort of set that was enumerated over all continuous restrictions, the bi-level enthusiasts in the crowd probably realized that this is a pretty natural fit for something like a column and constraint generation framework. So to scale this up to nonlinear function classes, that's kind of the pathway we've been doing. And it works really well in practice because even though the subproblems are MIP, again, because we're only looking at this very, very low dimensional MIP, they solve in fractions of a second. So we can do a lot of these iterations without this problem exploding. Okay, so some rapid fire empirics. So we test this approach on 3 data sets, 2 corresponding to consumer finance and 1 corresponding to content moderation. We use a set of actionability constraints from past literature that are these semantically meaningful constraints on the features. And we're going to audit a set of regions defined by demographic subgroups. So think of something like all Black female loan applicants. We're going to benchmark against these pointwise approaches. Recall a pointwise approach, you give me an individual, I tell whether or not it has recourse. And the only difference between these three columns is picking which of those individuals we want to test. So in this first column, we look at all of our training data, test all of those individuals. If they all have recourse, we say that that region is responsive, so everyone has recourse. If they all don't, we say that the region is confined, and if it's something in the middle, that we abstain. Region does the same thing, but we randomly sample data points from that region. You can imagine that as we increase the dimensionality of our data, this kind of slows down. You need to sample more data. And then score is kind of a simple heuristic where we look at the data points with the highest and lowest classifier score for these linear models. The intuition being if you're further away from the decision boundary, you have to do more work in order to change your outcome. We care about two failure cases. The first are blind spots. So these are settings where we say everyone has recourse, but in practice they don't. This could correspond to deploying a liver allocation mechanism that inadvertently denies someone a liver. By definition, our approach is never going to have this problem, right? We're giving nice global certificates, but these pointwise approaches can fail in pretty spectacular ways. So making mistakes on almost 40% of the regions that we're auditing. The other flip failure case that we care about are loopholes. So these are settings where we say nobody has recourse, but it turns out people do. This is important in content moderation, where we might want to ensure that people can't game their way past the spam filter. Again, by design, our approach is never going to have this failure case, but these individual pointwise approaches can fail. Great. So quickly wrap up. I like this paper because I think it's a better way to think about recourse in these policymaking and model development perspectives. But there's still a lot more work to do. In today's talk, I focused on linear classifiers. In theory, all of the machinery I talked about extends to any MIP representable function class, so decision trees, random forests, neural networks. The challenge is that the number of those continuous restrictions starts to explode, so you really need these column and constraint generation approaches to work in practice. We're also taking this for a spin on some real-world audits. So we're working with folks in Switzerland on using these for that liver allocation tool in the UK to help characterize what sort of individuals are being precluded. And then finally, even though I've been talking about this as a verification problem, you can also imagine this as a building block for actually being able to train machine learning models with these recourse guarantees. Great. So in the last couple minutes, I want to zoom out a little bit and talk about some kind of open research directions. And I'm going to pick on optimization. And really what I want to advocate for is kind of revisiting our role as optimization researchers and kind of the scope of problems that we can work on to help practitioners. So the picture I was taught as a PhD student at Cornell is that our role as OR experts is to come up with really, really good solvers. So given a well-defined problem, we come up with awesome solvers that can give us an optimal solution as quickly as possible. But anyone that's done consulting work or something that came up a lot in our interviews with practitioners is that's a really small piece of this overall problem-solving ecosystem, right? A lot of work goes into actually getting to that point where we have a concrete optimization model. Typically, that means an OR expert has to talk to a lot of different folks, each with different and potentially conflicting views of what the optimization problem they want to solve is. These decision makers might also do a bad job at specifying how they want to, the problem that they want to solve. And this came up again and again in our interviews. So we had people complaining that this whole process felt like a flywheel, because as soon as you were finished, a new constraint would pop up, and these projects felt never ending. It's happened over 99% of the time, and essentially, a really big pain point for these practitioners. So one direction I'm really excited about is building interactive or iterative preference elicitation for this optimization setting. So being able to help these non-expert users concretize the optimization problem that they're solving, even helping them navigate these multi-objective problems where they might have conflicting objectives, and being able to automatically generate portfolios of solutions to help them reason about these objectives without having to do these slow feedback loops with OR experts. The other thing is that, in practice, sending a problem to Groby for real-world problems is not enough, right? To be able to tackle the complexities of the real world, you often have to come up with, for instance, custom cutting planes or custom primal heuristics, maybe apply decomposition algorithms. And I think there's a lot of cool opportunities to revisit how we do this with a modern ML toolbox. So for instance, using tools like GNNs to identify block structures to exploit and automated Danzig-Wolf decomposition algorithms, or combining LLMs with evolutionary search to come up with custom primal heuristics or cutting planes for a given problem. And then even once we have a concrete problem with a rockstar algorithm, this validation loop is really, really key, right? And this is becoming an increasingly important problem because there's been a ton of industry interest in these automated modeling tools. You might have seen Gurobi has this automated modeling tool called Gurobot that came out last year. Microsoft has been working on these LLM tools for supply chain. NVIDIA is building out a whole team to do this automated supply chain modeling. So as we're getting more and more of these LLM-generated MIP formulations, it's really important that we have good ways of flagging uncertainty to users and making sure that they can validate that that optimization model is actually correct, right? And this is kind of another one of those examples where there's been a ton of work in the machine learning space on explainable ML, uncertainty quantification, appropriate reliance, but we just haven't had the kind of same interest in the optimization community, with the exception of this like really beautiful paper that I recommend from Guido Tack and Tim Dwyer at Monash University, where they built a user interface for helping folks debug how good a VRP solver is. But yeah, tons of open problems on how we enable non-expert users to validate these very technical artifacts being MIP models. So on that note, I'll end off, and hopefully we have a little bit of time for some questions before lunch.
Okay, let's think. Okay, any questions? Okay.
Connor, thank you. Just a quick clarification. So on the second problem, what you're calling fixed prediction, if I understood what you said, please correct me if I'm wrong, is I change a independent variable and the prediction doesn't change, right? And so the goal is now I'm going to search the feature space and try to find something that's a bit more representative. You mentioned the black applicant problem. Is that kind of broadly, did I understand correctly?
Yeah, exactly, right? Like, what actions can I take to reverse my outcome?
Okay, but it also, sorry, go ahead.
Oh yeah, and trying to characterize what individuals do not have any sort of recourse. So there are no action plans available to them.
Okay, and so the problem of, this also includes, for example, because this is something we see in practice a lot, where I think we talked a little bit about our talk, somebody will say, okay, I have this risk calculator for a hard condition, and actually I changed one of the covariates, and actually you expect the risk prediction to improve, but it actually gets worse, and part of it is because they're not sampling the distribution correctly. There's some correlation that they're not sort of attending, and what I've seen in the literature is that they, to overcome that, is they try to treat the covariates as like causal things, so I don't know if you could speak to that or like.
Yeah, so there's been a ton of work. I kind of brushed over it, but in algorithmic recourse, I mentioned there's like all these different classes of constraints folks like operate under, and I think the most promising one is you're embedding these actionability constraints represent causal kind of considerations. So if you have a good causal model, which is a big if, I think in a lot of these settings, you can embed that as a model to do better recourse plans that you would expect, even if this model changes over time, should be correlated with the right outcome.
Any other?
Yeah, your first topic seems like have some similarity with human factor type of study, like usability study.
Yeah.
So can you elaborate the similarity and the difference between a typical human factor type of study?
Yeah, I think they're very similar. So I'll say I'm a new joiner to the field of human factors in HCI. My background is computational integer programming, but I think it's the right toolkit for evaluating these systems and understanding their limitations and appropriate reliance. So the user studies look very similar to, I think, human factors. Our flavor is kind of this interfacing with optimization tools, right? So building these new systems that understand the underlying mechanics of an integer programming solver to be able to expose that functionality, and using LLMs as a translation tool. So that's more of like systems design, but I'd argue there are plenty of folks in the HCI realm that also work in that space. I think my contribution is, having done 5 years of learning integer programming, I have a kind of better insight into how to build these systems than more kind of general purpose HCI folks.
Okay.
So for the second topic, seems very similar to a lot of the stuff that's been done with global explanation methods, right? Like we've got rule list elicitation, we've got global tree search construction. Can you maybe elaborate a little bit, I guess, about what's the difference between what you're doing, or is it just like another way of forming global explanations for particular models?
Yeah, so I mean, recourse is also used as a tool for explanations. So I mean, the use case is slightly different. Like here, we're doing it to help people change their outcomes, but you could also imagine using that as a tool to understanding a black box model. The difference between a lot of work on these like explainability methods is that they're trying to characterize like a fixed output, right? Like this is the region where I'm going to get this response, this is the region where I'm going to get the other response. Here, it's a little gnarlier because we have these constraints on what actions people can change, right? And that's maybe a causal model. So it's not just like evaluating a function at a point, it's evaluating an optimization problem at this point. So it's, seeing if it's infeasible or not. So it's a little, from an optimization perspective, it's a little more complicated than these global explanation tools, at least the ones I've seen. But maybe we can chat more offline about it, yeah.
Okay, let's thank our speaker for an interesting talk.
Oh, okay, thank you.